Hi, welcome to lecture 23, Applied Optimization. There is no new material to be taught here. It's only going to be about problems. Uh, the idea behind these problems is using the tools that we've developed for involving derivatives in order to detect global minimum and global maximum points of a function, but this time applied to actual applications. So this is one example right here. I'm going to start with two very similar examples showcasing what it looks like and then have some more like word problems examples. So in this one, if two numbers x and y larger than or equal to 0 have a sum of 11, what is the maximum value possible for their product? And I specifically chose an odd number here, 11, because just to clear out any confusion, these numbers they do not have to be integers. They are not going to be integers because this is odd, but we'll see that happening. What is the idea here? You have two numbers, but they have a sum of 11. If one of them is very large, that makes the other one very small, and the product of the two things is actually going to be small as well. A small number close to 0 times another number that's going to be close to 11, well, that has to be small. So these two numbers, they must have a comparable size in order for this product to be the maximum value possible. And it's reasonable to expect that it should happen right in the middle when they're both 5.5 because they have a sum of 11. And that is going to be the case, but we have to use calculus to justify that. So what's the idea? Well, first of all, the two numbers are constrained to be 11 when you sum them up. This constraint is something that happens, and then we have a function of the two numbers that we can call p of xy. The function that we are interested in making as large as possible, maximum value. And it's the product function. That's why I'm calling it p. It's x times y. Well, what do we have to do? Because calc1 is about functions of one variable, but this is a function of two variables. We're going to need to rewrite this as a function of one variable only. And we have it right here because this constraint equation gives us y in terms of x. You can solve for y here, y equals 11 minus x. And then plug that back into here, into the product function. So now I'm going to be using some slight abusive notation here. I'm going to call it the same name, the p function, but now as a function of just one variable, just x. What does it look like? It's x times y, where y is 11 minus x. And I'm going to distribute this out to be 11x minus x squared. This function is the one that we want to be able to find the maximum value possible. That means global maximum value for the function. We have the calculus tools that allow you to do this, find the global max. But we also need to understand what is the domain for this. There were certain constraints in the problem. The numbers have to be larger than or equal to 0. So because x has to be larger than or equal to 0, this is one of the constraints involving x. Now we also have a constraint involving y. Y has to be larger than or equal to 0. In terms of x, this becomes 11 minus x larger than or equal to 0, which becomes x less than or equal to 11. Just move this x to the other side and then read the inequality in the other direction. So you actually have this function only between 0 and 11. What is the maximum value of this function? Between 0 and 11, including those two. We know this maximum must occur because the function is continuous, and this is a closed interval. This was called extreme value theorem, right? So we know this must happen somewhere. And remember, how do we do this? What are the possible locations where this max can occur? Critical points, or the two endpoints of the interval, which are 0 and 11. So we need to record the values of these endpoints, 0 and 11. Those are both going to be 0. Probably easiest to look at this expression for p in order to understand this. They are both 0. And then critical points. That's a very easy problem for this function. P is 11x minus x squared. P prime is going to be 11 minus 2x. This always exists for every x, but it could be 0 if you're talking about critical points. And you solve this, it gives you 11 over 2, 5.5. But always, you should always leave fractions unless you have to approximate numbers. Fraction is the exact. I mean, 5.5 would also be exact, but it's just cumbersome to work with. Fractions are preferred. So this is the only critical point of this function. We are then also going to record the value of the function at this value, at this 11 over 2. What is that? Just look, for example, in this expression, x times 11 minus x. This is going to become 11 over 2 squared. Those are all the values that we can find. That could be global max and global min as well. But the problem is about global max. Which one is the largest? This one. This is the largest possible product. That's the answer. This is the answer because the question was only asking for the maximum value of the product, and it was not asking about the two numbers. But if they were asking about the two numbers, well, we already have the x here. It's 11 over 2. And what is y? It's also 11 over 2 because the sum of the two is 11. So this is a very simple problem. I'm going to have another simple one right here. Very similar. So once again, two numbers larger than or equal to 0. They have a sum of 2 this time. This is the constraint. What is the maximum value possible for the expression below? This expression. This time it's not just a product. I'm giving a higher weight to the number y because y is to the 5th. So this time, how do we reason about this? Once again, at one extreme, if you make x as small as possible, x will be 0, making this entire thing 0. Similarly, if y is as small as possible, this is also 0. So the answer is going to be somewhere in between. But the y actually has larger power over x. So in order to make a product that's as large as possible, you probably want to give y a large value, although that's going to cause x to be small. So maybe the product will be too small. It's kind of hard to reason without using calculus. It would be basically impossible. But calculus gives us the way to solve this. So this is the constraint. We are gonna need to use this to solve for one of the variables in terms of the other. And the function that we are interested in this time is x squared y to the 5th. As it turns out, it's probably better for us to write this as a function of y instead of x, meaning that I'm gonna solve for x in the constraint. X is 2 minus y, and I'm gonna plug that into here. 2 minus y squared, y to the 5th. Why did I solve for x instead of y? Because the expression 2 minus y is appearing here inside of the square. If I had solved for y to plug it into here, then I would have to raise 2 minus x to the 5th, which is more complicated. Of course, it's all equivalent. It's going to give you the same answer, but this one is going to be easier to compute. So what is this function? You're going to have a y squared times y to the 5 minus 4y times y to the 5, and then plus 4 times y to the 5. That's the function. Similarly from before, y has to be a number between 0 and 2 this time. The sum of the two numbers is 2. So this constraint is obtained just like the previous slide. So you want to find the maximum value of this function on this interval. The values on the extremes, they are once again both 0 for the same reason as before. So you know that the optimal value is going to happen at a critical point. You need to find that, p prime of y. This is usually going to be the case, but not always. That the critical point is the one that gives you the correct maximum or minimum, whatever you want to find. That's not always the case, just normally. You have to verify everything. Okay, so in here, how do we solve for this? When is this entire expression equal to 0? You can factor a y to the 4th from it, which would give you a possibility of y equals 0, or If y is not 0, then you can divide by that y to the fourth, and now you have this equals 0, which is a quadratic equation, probably a little complicated to factor, but you have, so that means you have to use the quadratic formula for it, but that should be easy enough. So this is just what I'm doing here. 4 times 7 times 20 is 560. The square root here is the square root of 16. It's going to give you a 4. So this number becomes 24 plus 4, 28. Divided by 14 is 2. Or 24 minus 4, 20. Divided by 14, that's 10 over 7. Yes, this is the possible values of y where the critical point is. Well, those are 2 values for critical points. This one, the number 2, is already being considered in our analysis because it also happens to be one of the endpoints. But now we have one extra point, 10 over 7. What is p of 10 over 7? It is whatever. Probably look at this form of the function. We do need to compute this number. This is the number that we are looking for in the answer. It's going to be some combination of fractions. We don't have to compute this fully, but it's clear that it's some positive number as we expected it to be. It's a product of positive numbers. So this is the answer to this problem. How do we know this? We are comparing the 3 possible candidates for max that we found, and this was the largest one. So this is the largest possible value of that expression under the constraint x plus y equals 2. Okay, so now let's move on to some guidelines. What is going on in optimization problems? First of all, you need to identify all the variables. It was the x, y, and the objective function to be minimized or maximized. That's the x times y, or in the previous case, it was x squared y to the 5th. It's not going to be always that clear because they're mostly word problems. After doing that, you're going to also identify some constraint between the variables. In this case, it was x plus y equals 11 or 2. That's the one that you're going to try to use to transform the objective into a function of just one variable. Always you want to do that because we have tools for studying functions of just one variable in Calc 1. So identify the domain of that variable according to the problem restrictions. Going back, x and y had to be larger than or equal to 0, and that gave us an interval for x or y, depending on which one was the variable. And then use calc. Use calculus to find the min and max of that function in that domain. This is what optimization problems are about. Sometimes you may also have to justify, how do you know that the max exists? How do you know the answer that you found is the max or the min? There could be like an essay type of part of solving these problems. You have to write down a brief explanation, but we'll talk about that. Okay, so now this is more or less what the problems might look like. It's a word problem, and you're also going to see it involves some ugly numbers. Usually the fractions and things that are not they're not going to easily simplify. You're going to see many square roots and pi, and we'll see what I'm talking about. So here, a factory produces aluminum cans in the shape of round cylinders, and in each can, aluminum is only used for the circular base and also the lateral surface. The top is going to be some different cheap material. The area of aluminum surface for each can is always 100 inches squared. The problem is find the dimensions of the can, height and radius, that maximize the volume. So we are going to be constructing aluminum cans without including the top. And we have some area. The area of the base is pi r squared, if r is the radius. And what is the area of the lateral surface of the can, if you think about this? Imagine cutting it vertically somewhere and then opening it up. It becomes a rectangle. The height of the rectangle is h. if you call h the height of this can. And what is the length of the base? That would be the same as the circumference of the base, right? 2 pi r. This is how you find the lateral surface of a cylinder, like this, a round cylinder. So what they told us in the problem is that the sum of these two things, let me write 2 pi r h, is 100 inches square. This is how much aluminum we have for each can. But you have two variables to work with, height and radius. By changing accordingly the values of each under this constraint, you should be able to find the maximum possible volume for the can. It's easy to imagine that this is something that a factory might want to do, actually. You don't want to use too much material, but you probably want to make your cans hold as much volume as possible, or maybe vice versa. You want to minimize the material. This type of problem appears in real life. So this one right here is actually a constraint. It's an equation involving the variables r and h. Let's already go ahead and solve for one of them in terms of the other. It's probably easier to solve for h in here. H is going to be 100 minus pi r squared divided by 2 pi r. Just solved for h. But we don't have the objective function yet. What is the function that we're trying to find the minimum or maximum value of? Well, it's the maximum volume. This is the objective function. As a function of both r and h, what is it? How do we find the volume of a cylinder? Area of the base times height. But we don't want to have this function, objective function, as function of two variables. We want it as just one. And it's going to be r because we know how to find h in terms of r. Put this into here. So instead of pi r squared h, we're going to write pi r squared times this expression. And I'm going to simplify this as, let's see, 100 over 2 is 50. The pi's go away, so 50r for the first term. Splitting this fraction here. And what is the second term going to give you? R to the fourth divided by r is r cubed. There is 1 pi in the numerator and the factor of 2 in the denominator. 50r minus pi over 2 r cubed. Yes, okay. This is the volume as a function of just one variable. What are the restrictions that we have on this variable? This variable r. For this problem, I mean, it's always going to be different depending on the problem. For this one, probably the best way to think about this is like that. Do we have a minimum possible value for r? Yes. Technically larger than 0 strictly, but you can always consider 0 as well. You might always try to consider the endpoints as part of your problem if possible. R has definitely needs to be a positive number because it's a radius. So this is okay. But what is the maximum value possible that you can give this R? Remember that the total area of your cylinder cannot exceed 100. You can imagine that the maximum possible is when all of that area belongs just to the base, which you solve as this. Square root of 100 over pi, if you want to solve it like that. So I'm going to erase these equal signs. I'm going to write them as inequalities. The base can be at most area 100. If you have 100 for the base, then, well, there would not be any height. You don't have any aluminum left for the circumference, right? So this is the maximum that you can have as the area of the base. And solving for r here tells you that r is smaller than this particular value, 100 over pi square root. So this is just so you have a domain for your variable. And as I said, the two values are actually technically not achievable. If r is 0, there is no can, there is no cylinder. And if r is this much, then the cylinder just has the base and nothing else. It does not have height, so it would have volume 0. All right, so now we're trying to find the maximum value of this function over this. And actually, that's not what we're trying to find. We're trying to find the dimensions, r and h. find the dimensions that maximize the volume. So first find the max volume and then find the corresponding R and H. Okay. So the is the function. These are the endpoints. Let's find V prime. That's an easy one to do. 3 pi over 2 R squared. Yeah, this is V prime. I'm looking at V right here and taking the derivative. So on the one hand, this is what I was telling you, how to justify your reasoning. We know that max, let me write global max of V must occur on this interval from 0 to the constraint value. This is a continuous function on a closed interval, so there must be a global maximum value. On the other hand, it cannot be at the extremes because they give you V equals 0. This is where you would probably want to say if R is 0, there is no radius, so the volume is 0. And if R is the maximum possible, there is no height. Once again, the volume is 0. So the max must occur, but it cannot be at the extreme, so must be at a critical point. Well, points, we don't know exactly how many there will be yet. We'll find the critical points from V prime. So let's find them. V prime equals 0 is the equation 50 equals 3 pi over 2 R squared. So R is square root of 100 over 3 pi. I know I'm only taking the positive square root because, well, R is a radius, it's positive. This is the only critical point of the function in this domain, so it must be the one corresponding to the maximum value. It's very important that they were asking about max because, well, if they were asking about min, it would actually be 0, right? The 0 happens at the extremes. But they said max, and we were able to reason that it must be this one. So I'm saying this because we don't have to analyze the value of V at all these points to understand what it is, to compare them like we did before. It must be, the maximum must be at this value. And the problem was not even asking about this, the volume, the volume here. They were asking for the dimensions. So we just found one. We just found the value of R for that dimension, for the corresponding to the maximum volume. We're just missing the H. How do we find the corresponding H? Remember, there was a constraint between R and H. Here it is, 100 minus pi R squared divided by 2 pi R. So R squared is this, and then divide this by 2 pi R. Well, once again, here is R. So this is the H. The problem was physical. There is units, it's inches. This is units of length, right? They gave us area in inches squared, so these must be inches. And I'm not going to simplify the H. Those are the dimensions, optimizing the volume of this can. So let me move on to another problem. We're going to do the same thing for all these problems. Analyze carefully, identify the functions. This is a classical one. Farmer Brown has 200 meters of fence to enclose a rectangular region adjacent to a wall. No fence is going to go on the side of the wall, but one additional piece of fence must be present inside of the region perpendicular to the wall. See picture. So the fence is in red in my picture here. You see that there is no fence on this side here on the wall. There's no need for a fence there, but there is this extra piece inside. What is the largest possible area that can be enclosed by the fence this way? We're talking about the blue area inside of it. Okay, what can we make different in this problem? Why is this an optimization problem? What are our options? It's a rectangular fence. We are free to choose the width and height of this fence. It could be any rectangle. Only constraint is that the total length of the fence is 200 meters. How do we put this into equations? Constraint. How much fence is in the picture? You have one big side of y, which is the vertical side here. And how many x's do we have? There's actually 3 because there's this extra piece inside. It's 3x plus y. That's how much fence there is in the picture. That should be 200. So I'm already going to go ahead and solve for y in terms of x. We know that we're going to need that later. What is the objective function? The area as a function of x and y is the area of a rectangle, x times y. As a function of just x, though, it would be x times 200 minus 3x. The problem was talking about area, right? What is the largest possible area that can be enclosed? So we have the function. Do we have a domain for it? What is the domain? Once again, I'm going to consider the unphysical values at the extremes. X is a length. We know it has to be larger than 0. I'm also going to consider possibility that x is 0, even though that's not going to give us any meaningful area. It's going to be an area of 0, right? And similarly, y larger than or equal to 0. Why do I do that? Because then it's easy to say a maximum must exist, because now it's a closed interval, as you can see. After we translate this one for y, let's do that now. Here's the value of y given above as 200 minus 3x. If y is larger than 0, now you can solve for x here. X has to be less than 200 over 3. So the domain for the function is between 0 and 200 over 3. And you see what I meant. This is now a closed interval. Extreme value theorem tells you that the maximum must exist. We know it exists, and it's definitely not going to be at the extremes. Max A is not at x equals 0 or 200 over 3, because those are actually 0. A of 0 and A of 200 over 3 are both 0. We don't even need to calculate them in the formula, although it would be very easy. Don't even need that because we know what it means physically, looking at the picture. If x is 0, this rectangle has no base. It's very tall, right? The entire perimeter consists of only y, so it would be in here very tall, but no area. On the other hand, if x is 200 over 3, which is the maximum it could be, then there is no y. The rectangle in this case would be only the 3 pieces, 3 perpendicular pieces, but without any height between them. So once again, 0. And I told you this is usually the case. You usually don't consider the endpoints. You have to analyze them, but they're usually not going to give you your answer. So the max A must occur at critical points. Occur at critical points. A prime equals 0. A prime of x equals 0. So we need to find A prime. Here's A. What is A prime? X 200 minus 3x. Maybe I'm going to use product ruling here. Instead of distributing the x, which would be simpler, just to show you that you can also do it this way. This is what product rule gives you for this particular product. I differentiated the x first, and then I differentiated the 200 minus 3x. And you can see this is 200 minus 3x, so minus 6x. That's the derivative. Set that equal to 0. X is 200 over 6. Okay, we have x. What was the problem asking for? What is the largest possible area? So we're not done. We know that it occurs at this location when x is 200 over 6. but what is actually the value of A? Just look at the formula for A once again. Plug in 200 over 6. And I'm not going to simplify this. At least you should check this is a positive number. It is, right? This is smaller than 200 right here. So you know this is correct. I mean, it has a chance of being correct because the area is positive. So that's the answer, and we're going to move on. This is a classic one. You always see this in calculus textbooks. A line segment of length 1 will be cut into 2 pieces. One piece will be bent into the boundary of a square and the other into the boundary of a circle. What are the lengths of the pieces in order to maximize and to minimize the sum of the areas of the square and circle? So length 1, you're going to cut it somewhere. This is what's going to cause you to give you the freedom of choosing. You can choose this point to be anywhere. And you're going to create 2 geometric figures from each one of those pieces. One is a square, one is a circle. Okay, so let's give some names to the variables of the problem here. The things that we want to find are the lengths of the pieces, the two lengths here in which you cut the segment. If we call one of them x, the other one has to be 1 minus x. You could also call it y, but then you would write x plus y equals 1 and translate y into x as this, right? Because we know the total length is 1. So now this is a problem of one variable. The function that we're trying to maximize and also minimize, find the 2 possible locations for this function, is the sum of the areas. So first of all, we're going to have to figure out what is the side of the square here. If you're taking a total length of x and then bending it into 4 sides like this to form a square, then each one is going to have length x over 4. And the area of the square, product of the side lengths, is x squared over 16. That would be the square. What about the circle? So this circle has a circumference 2 pi r equals 1 minus x. That was the piece of wire that you had in order to form a circle with it. That's the circumference. So you can find the radius from there, divided by 2 pi. And then the area of that circle is pi times r squared. That would be pi times 1 minus x squared divided by 4 pi squared, which becomes 1 minus x squared divided by 4 pi. Okay, that's the area of the circle. I just want to double check with my answers. Yes, okay. So the area function, the objective function that we have in the problem is this one, the sum of the 2 areas. We're trying to find the values of x that creates the maximum value possible for this a and also the minimum. Two separate problems here. You should at least have a guess for this, at least for the maximum one. You may have heard already that the circle is the most, let's say, economical figure that you can form given a certain perimeter. The circle encloses the maximum possible area. If you want to find the maximum a in here, you want to essentially give all of this segment into the circle and none of it into the square. So I'm already telling you that we expect the maximum will be for x equals 0. X represents the part that goes to the square, right? So 0 for that and 1 for the circle. But the minimum is not necessarily going to be just with the square. Maybe a combination of square and circle creates a minimum. In fact, that will happen. How do we know for sure? With calculus. Okay, so global extremes for A I mean, we don't have an interval yet, but that's very easy to figure out. This interval, the location at this cut has to be between 0 and 1, or maybe no cut at all. So the extremes are included. This is a continuous function. This is a closed interval. We know the extremes must exist. Let's already analyze the value of this area function at the extremes. A of 0 will give you just 1 over 4 pi. And A of 1 is 1 over 16. As it turns out, you can see which one of these is larger or smaller. What is 1 over 16? It's 0.625. 1 over 4 pi is approximately 0.796. This problem in particular probably requires a calculator. I mean, comparing these two values is possible without a calculator, but after taking a derivative, you're going to see that we need a calculator for the other one. Let's find A prime to find critical points. So look at the expression for A up here. What is A prime? 2x over 16 plus, I'm going to use the chain rule for the second term here. 2, 1 minus x times minus 1. That's the chain rule. The minus 1 comes from the derivative of 1 minus x. And 2 is the power rule for the 1 minus x squared. All right. So I'm going to simplify this. You have x over 8 minus 1 minus x over 2 pi. Let me maybe put this into just one fraction. The entire thing divided by, let's say, 8 pi would be x times pi minus 4 times 1 minus x. So 4 plus pi times x minus 4 divided by 8 pi. Is this good? Yes. Okay, this is A prime of x. We set this equal to 0. Solve for x. So set the numerator equal to 0, and you have x equals 4 over 4 plus pi. Which, by the way, does belong to the location where you are interested. This is important to check. If this was a critical point outside of the domain that's meaningful for the problem, then we don't care. It's not going to have any influence in this problem. But this one actually does. This, whatever this value is, it's certainly a number between 0 and 1. You have it's positive, but the denominator is larger. So we need to figure out A of this monster number, this ugly number. And that one turns out to be approximately 0.0392. So you see, this is the one that I was talking about, that you need a calculator for that. Because I have to take this number and then plug that into the formula for A, not A prime, but A. This is the A. But okay, now we have the three candidates. Maximum and minimum must be among them. That's the Fermat theorem, if you want to give a name to that theorem. That tells you the global min and max of a function must occur at endpoints or critical points. So for max, we have the first one, as we already had told. I already had told you it would occur at x equals 0, meaning no square, only circle. But the min is actually not just square and no circle. It's a combination. Okay, but what were the corresponding values? Corresponding x values. At these locations. Remember, the question was asking for what are the line segments? The things that I circled in red, they are values of areas. Those are the maximum areas that you can find, total areas. But the question was asking what are the locations of the cut, or the length of the two segments corresponding to these values. So let's just write down what were the corresponding x values for these guys. For the max, it was x equals 0. And for the min, it was the 4 over 4 plus pi number. So for max, the two segments were 0 and 1. And then for min, we just found the x value was 4 over 4 plus pi. And the other one must be pi over 4 plus pi. Remember, those are the two segments with the sum of 1. So just to do 1 minus this one, and you're going to find pi over 4 plus pi. Those are the answers. So as you can see, these are kind of long problems. I think I'm going to be done for this video and continue doing this in recitation. But definitely practice a lot of these problems because there is no other than this recipe that I gave you in right here. There is no general recipe to solve these problems. The way that you get the constraint, the way that you get the extremes, the way that you justify that the value that you found really is the minimum or maximum, that's all going to depend on the problem.